All right, today we are going to talk about inverses of relations and functions. So inverses are very typical when you have relations and functions, and you can have an inverse of everything or anything, okay? So I want you to start thinking about maybe what your vocabulary explanation of what an inverse might be in your head before we actually get to it. So remember, a relation is a relationship between x and y, often written as a point, xy, right? We can make up any relationship or relation in the world. A function is when the relation has exactly one x to one y. So a relation that has unique x values. So when I say unique, I mean only one of them. Okay, an inverse, think about what the inverse of an addition problem would be. What do you use to undo an addition problem? Well, you use subtraction. So inverses are operations that undo each other, graphs that undo each other, values that undo each other. Think about the inverse of a positive 5 as a negative 5, right? They're opposites of each other. So a function is an inverse, is an operation that undoes another operation. So example would be 5 and negative 5. They add to 0, right? That's the additive inverse. Multiplicative inverse is when you multiply something by itself by 1 and you get 5. Okay, so inverses. The main thing you need to know about inverses is that x's and y's flip. Okay, so x's and y's switch. So they literally switch places. Your x's become your y's become your x's. Okay, they're, like I said before, inverses are opposites of each other. Okay, here, find the inverse of relation S, so it gives you a relation here, by interchanging the x and y values and completing the second table. So, like I said before, your x's become your y's become your x's. So here are my y values that are now going to become my x values. So my new x values are negative 1, 0, 1, 1. And I just got that from my y row in my table. My x values, 1, 2, 3, 4, are now going to become my y values. Okay, we found the inverse to this relation. Now, we can actually look at this on a graph as well. So I'm going to go ahead and graph this. So 1, negative 1. So here's my relation S. And they're just points, so I can't really connect them in any way. Here is my inverse. So negative 1, 1. Kind of looks like the same color, sorry. 0, 2. 1, 3. And 1, 4. Here is our graph of our two functions, the original and its inverse. So here's your original, S. And the inverse, we haven't gotten to it yet, but inverse we call S to the negative 1. Okay, that's called an inverse. So here's our original relation S. How do the two compare, right? Well, there's clearly symmetry of some sort, right? Here you could compare these inverse points to these pretty easily, okay? Notice how this is on the same position as the y-axis, okay? So what we call this is a symmetry along the x or the y equals x line. Okay, so think about the y equals x line. That's a slope of 1, a y-intercept of 0. So it's going up 1, 1, 1, 1. If I were to take actually take your paper and try and fold on that dotted line, your lines or your points, I wish I could show you this, your points, I don't think I'm going to be able to, are going to match up. Can we see that? Not really. So I want you to fold your paper along this line, and I want you to look at the points. So you might have to tilt your head, but your points will actually match each other, which is the exact point, no pun intended, of an inverse. Okay? So inverses, if they are actually inverses, they will be symmetric along that line. Okay, so we're going to see some other inverses. So it's asking us to graph the first one and then complete the second table in order to find our inverse. So remember that inverse is given by that -1. Oops, I wrote that wrong. So it's going to look like this. Now, we don't say f to the -1, we don't say f1, we don't say anything like that. We say f inverse of x. Okay. All right, so here's our f of x table, so our 3x minus 5. In 3x minus 5, we really just plug in -1 or -2 to 2. That's our normal x values that we plug in so that we can see the left side of the y-axis and the right side. Okay, so 3 times -2 is -6 minus 5 is -11. -1, -8, -5, -2, and 1. So we could go ahead and graph that. Okay, so there's our original graph. So now we want to see, okay, well, what is our inverse of this function? Okay, so remember your y's become your x's become your y's. So new x values are -11, -8, -5, -2, and 1. Our new y values are -2, -1, 0, 1, 2. And now we just graph. So -11, 2, -8, 1, -5, 0, -2. Does that make sense? Yeah, -2, 1. That's not a line. I had to pause to figure out what I was doing wrong, so this is fun. This is -11, -2. I'm sorry. -8, -1. There we go. I was very confused. And then 1, 2. Okay, so we have a slope of 1/3. Okay, so here we go now. This is the graph of our inverses. So see how here we have a slope of 3 over 1. Here we have a slope of 1 over 3. Okay, they're both positive, right? So we can't just say they're opposite reciprocals, but they are reciprocals. Think about what's going to undo 3. Well, the only thing that's going to undo 3 and equal 1 is 1/3. Okay. So, graph -1/2 x plus 6 by completing the table below. Okay, so we know our slope is -1/2. So like we saw above, it's probably going to be -2, but we just have to wait and see. So here's our first one. Oh, on our graph, we probably want to label, this is f of x, this is f inverse of x. We probably just want to get in the habit of labeling our graphs. So -2 to 2. All right, -2 times -1/2 is +1 plus 6 is 7. -1 is 1/2 plus 6, so 6.5. 6. 5.5. 5. Now f inverse of x. Flip your x's and y's, so 7, 6.5, 6, 5.5, 5. -2, -1, 0, 1, 2. So 7, -2, 6.5, -1, or yeah, 6.5, -1. Oh, I'm graphing the inverse, aren't I? Okay. All right, -2, 7, -1, 6.5, 0, 6, 1, 5.5, 2, 5. Okay, so here's our graph of our original. And then our inverse, 7, -2, 6.5, -1, 6, 0, 5.5, 1, 5, 2. Okay, so we can see that they clearly intercept at some point. And we do notice that our slope here is a -2, so down 1 over 2 will get you to the next actual point. Okay, so that's what a inverse will look like on a graph. Remember that they are symmetric along that line y equals x. So if you were to fold either of these graphs on that line, you should have points that match up. Okay, same thing on this one. If you fold it along that y equals x line, you're going to have points that match up with each other. So, finding an inverse algebraically, this is fun. So, we can actually find the equation of the inverse. So, like on here, we just had the table of the inverse. We can actually find the equation of this line. Okay, not only by looking at the slope, but we have to find the y-intercept as well. Here you wouldn't have, or you would have a decimal y-intercept, so it would probably be a fraction. Here you would also probably have a decimal intercept, so we want to actually know what the y-intercept is. So our first step to this is to interchange x and y. So x equals 8y minus 7. Now, we said that that was the main characteristic of inverses, is that x's and y's flip. Okay, so x's and y's flip. We want to solve the new equation for y. We know that linear functions have, in order to graph them, they have to be in the form y equals mx plus b. So x equals 8y minus 7. I'm going to add over 7, so x plus 7 equals 8y. Divide by 8. So I'm going to get that y is equal to x over 8 plus 7 over 8. And I'm going to do that so that I can clearly see my slope and my y-intercept. Here your slope would be 1/8 x, and your y-intercept is 7/8. We want to make sure that we're keeping in line with function notation, so I'm going to write this as f inverse of x equals x over 8 plus 7 over 8. Okay, is y equals 8x minus 7 a function? So would it pass the vertical line test? Well, it has a y-intercept of -7, a slope of 8. It's a linear line. It's going to go up and over for the entirety of its function. So yes, our original is a function. Here is the inverse of function. Well, I have a y-intercept and a slope. So that's also going to be a linear line, and therefore, passing the vertical line test, yes, would pass vertical line test. Okay, so next one, finding the domain and the range of an inverse function. So consider the function 2/3 x plus 4. Okay, linear line, right? Find the domain and range. Well, if it's going forever to the left and forever to the right, then our domain and range are -infinity to infinity. And our range is also -infinity to infinity because it's going down forever and up forever. Find f inverse. Okay, so we switch our x's and our y's, and we solve for y. So subtract x, or subtract 4, x minus 4 equals 2/3 y. I'm going to multiply by 3 to get rid of my denominator. So I'm going to be left with 3x minus 12 equals 2y. Divide by 2, and you're going to be left with y equals 3/2 x minus 6. We want to make sure we're staying in the normal notation, so f inverse of x equals 3/2 x minus 6. Okay, this still a linear line, so our domain and range are always going to be -infinity to infinity for linear lines. And linear lines' inverses will always be functions. Now, the way that this changes, so I'm going to give you another example. I'm going to give you a graph, and that's a 2. The domain of this graph would be 2 to infinity. The range of this graph would be 0 to infinity, because the lowest we go is 0 on the y-axis. Now, its inverse looks like this. Its domain is 0 to infinity. Its range is 2 to infinity. Notice how, here's your original f of x, here's your inverse f inverse. Notice how your domain and range literally swap. Think about y. Your domain is all your x values, your range is all your y values. Here, if we know that x's and y's flip, then we also know that domains and ranges, I can't speak today, domain and ranges also flip, okay? Because domain represents x, range represents y, okay? All right, something to keep in mind. We're not going to do that probably till next semester, but I want you to see that this is maybe how something that's not linear looks. Okay, so in order to prove that two functions are inverses of each other, we can do compositions. Okay, so if you think back to 2.2, we did composition of functions. Here's why. Here's an actual use of composition of functions. So for the function f of x equals f of x plus 11 and 5x plus 11 and f inverse of x equals x minus 11 over 5, find f inverse of f of x, and then find f of f inverse. Now, there's a rule in math that says if f and f inverse are truly inverse functions, then the composition forwards and backwards will both equal x. Just x, nothing left over, no coefficients, nothing, just one x. So we are going to check that these two are actually inverses of each other. Okay, and this is a proof. Okay, so I'm going to rewrite this as f inverse of f of x. Remember that open circle means composition. I know what f of x is equal to, so I'm going to replace it. So f inverse of 5x plus 11. This tells me that I replace x with 5x plus 11 in my f inverse function. So here I see an x. I'm going to replace that with 5x plus 11. I don't need parentheses because I'm not multiplying by anything. I can simplify the top. 11 minus 11 is going to be 0. 5 divided by 5 cancels, and you're left with x. So we have proven that f inverse of f of x is just equal to x. Now we need to prove the opposite way. We need to prove that f of f inverse is also x. So I'm going to rewrite it, f of f inverse of x. We know what f inverse of x is equal to. It's equal to x minus 11 over 5. So f of x minus 11 over 5. So this tells me we replace x in my normal function with x minus 11 over 5. So I'm going to get 5. This is multiplying, so I'm going to have a parenthesis. Couple different ways that you can do this, and you're probably already thinking about your next step in your head. We could distribute 5. However, a main mistake that I see with this is that if we distribute 5, this is 5 over 1. So remember, multiplying fractions, you multiply straight across. So you would only multiply the numerator by 5. The denominator would be multiplied by 1 because this is 5 over 1. Okay, so you'd get 5x minus 55 over 5. Here's why I don't like doing that. Here, because we're multiplying, if I multiply without actually simplifying, I get this. Okay, same thing as up here, your 5 over 5 cancels, and you're left with x minus 11 plus 11. Now, if you did the 5x minus 55 over 5 plus 11, that's fine. You would simplify your 5x, you would simplify your 55, and you would get x minus 11 plus 11. Or you could just do this. Negative 11 plus 11 is x. So we have now proven that f of f inverse of x equals x. So yes, because f inverse of x, f of f inverse of x, and f inverse of f of x both equal x. Oh, I'm so sorry you couldn't see that. Okay, so yes, we actually proved, right? We followed the proof. It told us to do f inverse of f of x, and it told us to do f of f inverse. We did both of them. We got out exactly what it told us we should get out, right? This should equal x and this should equal x. Well, it did. So now that we've proven both of those and done it forwards and backwards, we've actually legitimately proven that they are inverses. Okay, move on to 2.3 assignment in Canvas and let me know if you have any questions.